making process at the edge devices. So the essence of this kind of lightweight device, lightweight machine learning models is required. So one such thing is weightless neural network. I have discussed stuff of this session. Now let us see some of the work which we carried out during our PhD. We will discuss. If you see the, you already know that how the decision tree is constructed, and you want to ask the question that how we can generate these decision trees. Also, the main aim of the decision trees is once you construct the decision trees, you can generate the rules. The question is, can't we get the rules directly from your data? Further, so we can pose it as an optimization problem and we can solve it. When you are posing it as a problem, optimization problem, this becomes a hard problem, and this hard problem can solve using any one of the bio or nature inspired algorithms. But towards that, we use the one of the algorithm which is based on the spider monkey. So we have used the spider monkey optimization SMO algorithm for generation of this rule process and all. So let me explain this, how we have generated these rules and all in the current session. So if you look at, so this is the same experiment we have carried out for the diabetes data. So which will have 8 features. 1 second. So which will have 8 features, and those 8 features I have shown in this slide. So if you look at the each and every, the feature is hard code encoded as a called a 3 quadrants. Okay, 3 quadrants, 3 subparts or sub regions or sub components. So if you look at under the pregnancy, we have 3 sub components, and it's divided into 3 parts. So what is the first part is talking about is a flag value. The pregnancy count is now we are decoding encoding as a, the first part is talks about the flag triplet. In the triplet, the first is a flag and the second is the lower bound and third one is the upper bound of your feature value. So the 1, 3, 10 we can interpret as a if the so and so feature value is between certain ranges 3 and 10. So the lower bound, upper bound will decide the ranges. So like this, you can hard code and these ranges, and by using this SMO or any it's a genetic algorithm PSO. So if you take any bio-inspired algorithm, so we are trying to optimize these boundaries. We are trying to optimize these what is called we try to converge in a value where we will these values will produce in a good accuracy on your data set. So on the other hand, if you say the glucose, the 0 and 71, 130, what does it mean? That if there is no 0 means there is the particular feature is won't be a part of your rule. So we have to if you take the rule, it will have both antecedent and consequent part. In the antecedent part, we will have what is called features which will have whose flag value is 1. So in this case, the flag value is 1 present in the pregnancy count, and there is another is called the diastolic blood pressure, and there only you will have 2 flag values are 1. So remaining all are 0. So it means that's the reason in the rule antecedent part, means if part, you will have only these 2 features, and then you will have a class is equal to negative. Means we are classifying that if so and so condition is satisfied, they are belongs to negative category. The question is, how do you get this class category? We got the if in antecedent part. How do you get the consequent part? How can we determine this consequent part? How can you determine? It's very easy. So what you have to do, you have to segregate your data into class level. Then once you segregate the data into the class level, then you can. So if any rule is being generated from positive class, it all belongs to the positive class. If any rule is being generated from negative class data, it is a negative class. So means, so if you want to get the positive class rules, you have to apply, you have to generate the rules from the positive class data only, like that. Then the consequent part is fixed. Now the same thing I shown here. So every time what we are trying to do that, we are running the spider monkey algorithm. So for the generation of the rules, and to evaluate which one is the rule is the best one or not, by we can evaluate it by its fitness function, because every every optimization algorithm will have the corresponding fitness value or objective function. So that will determine the quality of your solution. What is the solution, OEM? I am looking for rules. So it means that how we are generating the rules by using SpiderMonkey. So each rule is nothing but one SpiderMonkey, and this SpiderMonkey will initially will have some random values, and it is striving for a based on the SMO algorithm rules. It will search for the particular food in some particular direction, and by creating the groups and subgroups and like that. So then it will find out the best rules. Okay, it will generate the best rule, or for the current iteration that may be the best rule. But once we get there, that means once this SpiderMonkey will identify the food, means it's nothing but we found the solution that is the best rule. So like that, in every run we will get the one solution. What is the solution? One rule, right? Once so how do we evaluate whether it's a good one or not, bad one? By using the fitness function. Now choose the best according to the maximum fitness value. So we want to it's a maximization problem, so that's the reason. So we will identify the best rule which will maximize our fitness value. I will discuss what is the fitness function we have proposed. So once the SM rule miner selects the rule, it updates the training data set, because already first we have used this data. From this the ruler one. So on this data I applied SM SpiderMonkey optimization. So this SpiderMonkey algorithm has generated one rule. So it has given one rule. Now this rule is generated from this, right? So this is the D1. So now, so this data set has to be updated. You will get a data set D2. Again you will apply SMO. You will get R2. The question is, what is meant by update over here? What is meant by update? So what the update over means, remove all the tuples satisfied by R1. Because in this you might have some two, suppose there are 100 rows, 100 tuples are there. In this 70 has satisfied this, means with the help of this rule, you are classifying this 70 tuples properly. So then remaining 30 will come over here. So the remaining 30, now data size is 30. So like this, you are slowly, the next time it may be 10. So next rule R2 will be generated after updating. So you can say that you can stop or you can continue further. So like this, you will have to apply the SMO for multiple times. So initially you will get R1, then you will get R2, then you will get R3, something so on. So this will create for positive class. Similarly, you want to do for the negative class also. It will create another set. So R1 plus, this is R1 plus and this is R1 minus, R2 plus and R2 minus, okay, R3 minus. So this will call the rule set. So the rule set will be generated in that fashion. Okay. So once SM ruler selects the rule, it updates the training data set, as I said, by eliminating all the records covered by that rule. If you look at it closely, observe. First we will apply this, then the computer fitness value, pick the best, the rule corresponding to this. Then what we are trying to do? Then we are updating the training data set. We are updating the training data set. So this updated data set is used to generate the next rule in the next iteration. Exactly. So this process is repeated until the stopping criteria is reached. The stopping criteria could be like if your number of records in your updated data set is follow certain threshold. Suppose after updating, after updation, suppose your rules, your data set is having only 5 tuples. So you kept the threshold 10, means, so 5 is less than 10 means, so you can terminate your algorithm whenever you will have a data set which contains the number of tuples below 10, then you can stop your algorithm. So like that you can keep some kind of termination conditions to eliminate to what is called
to come out from this particular algorithm. So this process is repeated until the stopping criteria is reached. The same thing. So finally, the generated rule set is tested on the tested data. So like it, once we generated such kind of rules, so these rules will be tested again as the corresponding data set, tested data set. Of course, here we have used a tenfold cross validation. So I already discussed what is the tenfold cross validation. So your data set is being divided into 10 equal parts, and one part is used for testing, and remaining 9 parts are used for the training, and this process will be repeated for the 10 times with the different training and testing data sets. Now, if you look at closely observe the fitness function, here we have considered the geometric measure and also called. So this geometric measure will provide the performance of classifier performance, the rule performance towards the accuracy or sensitivity and specificity. How many tuples it is being classified properly. And this another part, if you look at MIR, what is this MIR and comprehensibility? This MIR and comprehensibility will talk about the rules, the number of rules and the compactness of the rules. So what I ideally want is, even though the rule should be very small, and it means the rule should be very compact. Even though it is compact, its performance should be the better. So it means I want to balance. It's a multi-objective. So I want a rule set which has a both compact in nature, and it also should produce the produce the good performance in terms of accuracy and all. So that's the reason we have chosen this criteria function, objective function. So in that objective function, we have consider the geometric measures. What is this geometric measure? Is the geometric measure of the positive class and the geometric measure of the negative class. What is the geometric measure of the positive class? The measures which will speak about the positive class, like precision and recall. So the geometric measure is the square root of precision and recall. And say on the other hand, the quantities which will speak about the performance towards the negative class is called inverse precision and inverse recall, and we calculated it's called the geometric mean as a square root of inverse recall and inverse precision. Yeah, that talks about so means we want to classify both the positive and negative class properly. So I don't want to focus one class, but I want to classify like this. Then MIR, mean interval range. So what should be the ranges? So the ranges should be come to the upper bound, and the ranges means the lower bound, upper bound. So what are the ranges of your features? You should also fix them very properly. And the comprehensibility means the comprehensibility will talks about the length of the route. So this also we should minimize. Okay. So that's the reason the first performance I want to maximize, and the MIR I want to maximize, and the comprehensive I have to minimize. So overall I have to maximize this thing. Okay. That's the reason. So W4 into MIR minus, because I want to minimize the comprehensibility, and it's nothing but minus comprehensibility I want to maximize. If you put a minus, then it has to maximize. Both are same. Minimizing the comprehensibility or maximizing minus comprehensibility is both are same. Right. Okay. This is how we have to calculate. So this is some experimental analysis how we have experimented and all. So how we have calculated mean rule length. What is the length of the rule is calculated as the number of features in the antecedent part, the if part, by the total number of rules. And these are some of the hyperparameters. So some are hyperparameters of your spider monkey algorithm. It has a 5 hyperparameters, and these 5 hyperparameters have been, we have to fine tune, because in the soft computing you have to fine tune, because it's a machine learning also. You have to fine tune all the hyperparameters, because it varies from the problem to problem. If you take ANNs, weights, if you take KN and K value, all these are, there's no global value which accepts for all sort of problems. So that's the reason these hyperparameters will be fine tuned specific to your application. So for my application, for my problem, so I fine tune, and these are some of the plots why I have fine tuned, how I fine tuned, I explained here. Okay. So these are the values which I obtained after fine tuning of my both weights and these hyperparameter values. So these are some hyperparameter values that speaks of the fine tuning of fine-tuned values of these parameters. So after fine tuning of above said parameters like SMO as well as the weight parameters, let's see the performance. Okay, so in each fold, because we have followed the 10-fold cross validation, so it's one of the what is called the way we can split the training and testing data sets. Okay, Now, by using 10 FCV, 10-fold crash validation, so this process we have, so this is called one fold. In every fold, we will run one SMO algorithm for both positive and negative class. Imagine for one positive class, first I will take whole data set, then I will run spider monkey algorithm, then you will get rule R1, then you will update the data set, then you will apply SMO, then you will get rule R2. So like this you have to repeat. Means in this case, in the first fold one, 2, 3, 4, how many rules are there? So that many times you have run my SMO algorithm for both positive and negative class. So the number of rules I have generated is 4, and mean rule length means what is the MRL? The average, what is the annual average rule length is 1.5. Okay. So like this we have found the results for 10 folds, and we took the average of all those values, and at the average, and it means that an average, when I'm talking about 10 folds, the an average, the speed, the number of rules which are generated by this algorithm is 4, and the average length of the rule is 2.025, something like that. And when I'm looking at the performance accuracy also, we got nearly 90% of performance achieved with the help of this spider monkey algorithm. We achieved good accuracy also, nearly 90%. Now, this is, I think, this is all the algorithm, yes. So, you are all familiar with the ID3 and C4.1 quarter. What are they? They are all decision trees, right? So, once you get the decision trees, so these are already discussed. Once you get the decision trees, so what these decision trees are? These decision trees are converted into the rules. Once you consider the decision tree, you can generate the rules very easily. The number of rules are nothing but the number of the leaf nodes. So this is an SMO is an algorithm that will generate the rules directly without constructing the decision tree. So that's what I said. Okay. So here we are generating the rules without constructing the decision tree. Obviously, we have compared. So if you look at it, when I'm comparing with the other decision tree based or rule based classification algorithm, if you look at, so even the spider monkey algorithm is performing better when compared to other algorithms also. The performance is nearly 90, and the average rule length is nearly only 2, and an average 2. So those who are interested in this article, you can go through this article in the Computers in Biology Medicine, which is published in my part of PhD, and it's a very good journal. The impact factor is, I think, nearly 8, I think 8, yes, 8 impact factor journal it is. So you can refer the following, so it's published in the year 2007. So Computers in Biology Medicine, the title is SM Rule Miner, Spider Monkey based rule miner using novel fitness function for diabetes classification. So you please refer this paper, those who are interested, how we can. So there is another thing. So where if you look at in the literature, people already used this bio-inspired like PSO, artificial B colony, and anti-colony. So because these are natural bio-inspired algorithm can be used to solve different kind of hard problems. Okay. So the similar way we have used the SMO miner we have proposed, and we got succeeded in that. Okay. So this is the this comparative analysis says that we are getting better results than other state of the art. Of course, there is another algorithm which is invented by which is proposed by genetic algorithm. Even though their accuracy is good, if you look at their accuracy is good, but still, but even though they have good accuracy, but they fail to get the other two parameters. So if it's the number of rules and mean rule length, in that other two parameters, even though there is a 2%, there is nearly 2% of percentage difference is there, but on other parameters we have this spider monkey is performing better. Okay, so we have used different kind of analysis for comparing this model. So when you are writing any research article, you have to always do this kind of state of the art comparison. So in which year it is published, and how your algorithm is different from them, how your algorithm is performing better than them. So you have to make this comparative analysis. Otherwise, it is getting acceptance in any journal conference is very difficult. Especially I'm talking about SCI journal setup. So okay, right. So with this, I'm closing my session. So guys, if you have any doubts, please let me know. And at 3:30 onward, I think there is a valedictory, and afterwards you will have an exam assessment test. So all the best for an exam and all. Okay, guys, if you have any doubts, please let me know. So we can also extend this problem by introducing the fuzziness. So this is a fuzzy rule miner. So if you look at the fuzzy rule miner. So here we have, so what we did, we have discretized information. So in the decision trees, we have seen if there's a numerical data, what we did, we have done some discretization, right? The same thing we did here, discretization. So once we did, and we also use a new technique is called, so we look at this particular thing, we have used adaptive boosting algorithm. So what we are doing in the boosting algorithm, if there is a weak learner, we are gradually improving in a sequential fashion. In the similar way, if there is a weak rule, so same thing for the rule. If there is a weak rule, so this rule is getting modified and this rule is getting appended so that at the last we will get a strong rule. So from the weak rule we are generating the strong rules. So that technique we have applied. So we have combined the adaptive boosting and technique for the rules. We apply the adaptive boosting technique for the rules instead of the classifier. Okay. So this paper is also published in Applied Soft Computing. So guys, and if you have any doubts, please let me know.
Sorry to interrupt you, sir.
Just one second. I'm like, yes, sir. Tell me, sir.
Sir, how much time it takes, sir? Can we start the valedictory?
Yes, sir. It's over, sir. I think.
Okay.
Start your valedictory.
Okay, sir. 2 minutes, sir. Thank you, sir. Meanwhile, you can close the session, sir. Topic what you are discussing about.